What's up, everybody? In this part 2 of our MPC playlist, hopefully this will be a playlist at the end of this week, right? And or in the next week. And here now we are specifically look at nonlinear control problem, right? And this is our second motivating example, right? And in this example we are going to see how we are going to employ MPC algorithms for a simple, right, but very important, right, nonlinear state dynamics. Okay, so this is our problem. X equals x squared plus u, right? I mean, this is because of this term. This is nonlinear, right? All right, and well, let's start from scratch. Okay, and we are going to discretize this plant. Okay, just step by step, one by one, let's analyze that. Okay, just let us use forward error approximation, right, for this derivative term. Here this is we get, and let's arrange the terms. Okay, here this is again we have, and let's isolate x of k plus 1, right? At the end, this is what we have. However, right, unlike the previous examples, I mean x of x and u of x, where x of x and u of x were they appeared in nonlinear, the affine form, right? And this is here we can see this term is nonlinear. All right, so how would we solve this problem? First of all, we are using UMIP, right? And basically we are employing convex optimization algorithms to solve our problems, right? And in the previous problem we didn't have any problem with that because the problem itself was linear, meaning affine. So there was like inherent convexity built into our previous problem, but now we need to quote-unquote convexify our problem, right? We need to employ some type of approximations, and for this here, right, and Taylor approximation, like as old as it gets, right? And algorithm or method we are going to use. Okay, and we are going to linearize our nonlinear term in for a given point, right? Okay, and we will hope that this linearization will result in something correct at least at the neighborhood of that given point, linearization point, and we can also say like operating point or something. All right, I mean, let's again to remind ourselves what the Taylor approximation was, right? And let's look at this problem. F of xy, this is a function, and x times y. All right, so let me also indicate, get the Taylor approximation of this function at this point, x bar and y bar. Okay, all right, and okay, well, first, this is our first term, right? Just evaluate the function for the given points. Okay, and then like this is like the Jacobian, right, that we used to consider to use, to get the Jacobian matrix, right? And then we would find the eigenvalues, and if they are like stable, we would conclude, hey, all right, in the neighborhood of that region, at least we know that it's stable, the given nonlinear system is stable. So we have talked about this, we seen about this, right? All right, this is like the Jacobian matrix, right? And of course this is scalar, so this won't result in a matrix, but we will rattle we will use those ideas to like n-dimensional problems, right? Okay, we are again looking at one-dimensional problems. X dot equals x square plus u. This is, I mean, we have only one state, right? Okay, and here we can see the second term. Just get the Jacobian and or take the derivative with respect to x and compute it for x bar and y bar, right? This value I'm talking about, and then times x minus x bar. This is this term. Okay, this is the second term, and finally our like third term, right? Okay, here basically the same, right? The symmetric operation, and we have these three terms, but also we have higher order terms, right? But like most of the things, right, we ignore that. And okay, so for this specific problem, let's try to solve that and obtain the analytical result by hand, right? Okay, x times y. Okay, just evaluate for x bar and y. Okay, this is what we get, right? And this term, right, just take the derivative with respect to x. Okay, x times y. Take the derivative with respect to x. What would we get? We would get y, and then evaluate it for the given x bar and y points, right? This is y bar we get. Okay, and here we can see that, and also times x minus x bar. Okay, everything is in order, right? And again the same idea, same thing for take the derivative with respect to y and evaluate it for in x bar and y bar, right? The point that we are kind of linearizing around. Okay, all right, everything's great, and this is the whole expression, and those two terms they cancel each other out, and this is what we have. Okay, and okay, and you would it I feel like you're thinking, hey, what does this have to do with our like the original problem, right? And actually it has a lot of things to do with that, and because we have x of k times x of k. Okay, quadratic term, right? Let's consider x of k as x for this problem, right? Like we see in this problem, and let's consider this as y, right? And also x, let's call it x bar of k, and also again x bar of k, and let's call it x bar, and let's call it y bar. Okay, and if we employ this renaming, right, we would get basically this, right? Okay, this, I mean, let me highlight it with another color. Okay, this is what we get. Okay, so what I'm trying to say is this: you have this nonlinear term, right? Okay, by using Taylor approximation ideas, right, linearize it, right, and by linearizing you get linear or affine terms, and affine terms are the terms that you can use to impose your constraints whenever you use convex optimization algorithms. Okay, and basically take this term and change that with that term. Okay, so your CVX or YOLMIP or any other like convex optimization solver will be able to solve that problem for you. Okay, and maybe it would be better for us to just, for the sake of completeness, right, let's write this maybe not like this. Let me get another color. Okay, and let me copy this expression. Okay, copy and paste. Okay, delete the unnecessary things. Okay, and let's one more time, let us copy that again and paste it. right? So let's delete this term. Okay, let's get a little bit space for ourselves. Okay, just look at this place. All right, we are just going to write this expression, okay, minus x of k square, okay, plus 2 times x of k times x bar of k. Okay, and now you are like, hey, what is x bar of k? Well, maybe we never talk about something like this, right? And okay, whenever you have nonlinear optimization problems and you want like to use MPC algorithm, okay, so let's say you have this, look at this part, you have x1 and x2 and you have u1 and u2, right? Let's say, right? And since your problem is nonlinear, or let's consider this the case where you are looking at a nonlinear problem, right? On top of having those x1, x2, or x1 trajectory, x2 trajectory, u1 trajectory, u2 trajectory, right? You would have 4 trajectories, but on top of that, you also have x1 bar, x2 bar, u1 bar, and u2 bar. Okay, all right. So the dimension, or this is the number of decision variables that you would use to optimize your problem, basically doubled in a way, right? In a sense. Okay, all right. Just I'm trying to talk in as simple as possible, right? Okay, so we will be able to solve this problem, and believe me, it is not that different compared to what we have seen in the linear MPC problem. Okay, all right. So, but before moving forward, let's look at this for the sake of completeness. Error approximation of this three-term function f of x, y, z, right? Okay, and basically again you would have, like, I would say zeroth order term, right? And then these three, like maybe I should do something like this, and first order terms, right? Okay, so I just wanted to make this clear. And again, let me tell you this, you can use easily, this type of computations are something that you are able to do, but depending on the expression that you have, these type of computations can be really annoying, right? And as an engineer, I would suggest you to employ some type of symbolic toolbox to deal with those type of annoying expressions, right? Okay, all right, just want to make that clear. So okay, basically this is our problem now, right? Now what we are going to have, x underscore rec, right? And also x bar underscore rec, and u rec, and maybe, yeah, we could also write down x bar underscore rec, but the only term that are u only appeared affine manner, right? In an affine manner. So we don't have any nonlinear term that has u in it, basically. So that's why we don't have also u bar rec. We don't need to define that, right? Okay, for example, I was kind of generalizing when I say whenever you have a nonlinear problem, you have x1, x2, u1, u2, right? And directly you would have x1 bar, x2 bar, u1 bar, u2 bar. For example, if you don't have u1 appearing in any nonlinear term, you don't need to employ or introduce u1 bar trajectories into a problem. It's basically, right? I should make that clear, and now it's clear, I guess. Okay, so let's finally, this is our problem, red circled expression. And let's go to MATLAB. Okay. Control up. Okay, so let's clean everything. All right, again I am looking at my screen to see if you're able to see that. Yeah, you're able to see that. Again, n equals hundreds, and these are again arbitrary values that you can change, right? And these are sampling periods. Again, we have u vec, x vec, or u trajectory, input trajectory, state trajectory, and also x bar, right? I should have written x bar vec, but you get the point. All right, and if you look at the expression that I written on the tablet, just look at this expression. Look at this expression, right? And let's just memorize that for a second, right? And let's go back to tablet and see if they match, right? Okay, this is this blue circle term, right? And this is exactly equals to the expression that you see on the MATLAB screen. Okay, all right, let's go back to MATLAB. Okay, and we employed the x of k squared expression. We employed Taylor expansion around x bar points basically, and we get this. So first of all, x bar, again, notice x bar is not our decision variables. We haven't defined it that way, right? We define it as random, just random numbers, right? And we are not going to solve this problem by changing x bar variables. However, first we are going to define x bar randomly, right? And then we are going to solve x vec, or state trajectory, and input trajectory. Okay, and then we are going to get the solution of our x vec. We are going to assign to x bar, right? And x bar, again, it's a vector of numbers, right? Okay, and then by using that updated x bar, we are going to solve for, again, x vec and u vec, and this process is going to iterate, right? And we are going to end this process whenever x bar stops changing, right? Okay, so since this is a nonlinear optimization problem, in a way, we are employing a type of alternation technique, right? Okay, all right. And again, since this is nonlinear and since this is non-convex, we don't have any way of knowing that whether the solution that we obtain is like the optimal one. As is the case with any other non-convex problems. But depending on the problem, probably what you will have is something that you will be comfortable with, right? If you're not comfortable with, you will try to maybe start from another random points, your x bar, I guess, trajectory. You would use other random variables. By the way, you can also, since our initial point is, since we want our vector to go from 10 to 0, right? You could also easily set something like within space from 10 to 0, like, right? You can, maybe I should write something like this. Just give me a second, right? Within space, right, from 10, because initial point is 10, right? And we want it to go to 0, right? And how many time steps we have? Like 100. Okay, all right. Maybe that would be a better way of picking our x bar initially. All right, let's solve this problem. I think everything is, I mean, the only this part change compared to the previous problem. All right, let's run it. Yeah, you are able to see that, right? I mean, we just run it for 5 times, but we could also easily run it for 10 times to see the convergence, right? And I feel like I should run it. Yeah, wait, just let me do this. Okay, just okay, let's run it again, right? Okay, I mean, I just, pause the video and think about something. For example, you can see, you just saw rather successful in each iteration. First you see successful solved, and the next iteration you solve infeasible problem, right? Maybe I should make it one more time. You see infeasible problem, successful solved, right? Okay. I mean, first I thought this might be a problem in my, construction of the problem, and then I thought, since we are using, alternation technique, this might not be a problem, right? And because I expected, to see like successful solved in each, time step. Okay, so anyway, here we have, what we have is this, right? And again, the state trajectory goes to, 0, and this is our input signal. And just for the sake of completeness, let's use like LQR type of, this quadratic cost function. Let's run it. Okay, of course this is a harder problem. Yeah. Okay, and I think what we need to do is something like this, but I'm kind of scared because it might take way much more time. Okay, let's try to look at the solution. Okay, all right, this is what we have. And again, maybe like do it for 300 steps, and maybe then we will see a like clear convergence, because we haven't seen the convergence to 0 again. Actually, yeah, now that it totally makes sense. Yeah, we are able to see that. Okay, but for the sake of completeness, I'm going to pause and solve for 500 times. Okay, I just, and I just solved for n equals 600, and it is amazing, right? You should be, I think, impressed by that. I mean, we are just solving in really, so for, I mean, 1200 variables. I mean, we just found more than 1000 variables, right? This type of optimization problem, and you are running this on your desktop computer and in a really small amount of time, right? And this should, I think, impress you a little bit, right? And this is a, like, we employed quadratic cost function, and it is almost like the Break-Strong, Break-Strong cron problem or something, kind of, the solution of it is similar to that problem. And yeah, this is what we have right now. Here we can see state trajectory starting from 10 and converging to 0, right? And in a manner that is not like trying to go to 0, right, immediately, because we are trying to use as small input u as possible, right? Okay, right, and this is for nonlinear 1D nonlinear 1D problem. And in the, hopefully in the previous video, right, by the way, you are I mean, this maybe, let me make it zoom out a little bit. yeah, this is like 30 lines of code, right? And we are able to solve this problem. And again, this is a motivating example, but it is significant, I think. And in the next video, hopefully in the part 3 of our MPC playlist, we will be looking at a nonlinear problem where we are going to use 2D and maybe in the later videos 3D or something, nonlinear problems, right? Okay, all right, that's it, and thanks for watching.